Hello friends, welcome to the welcome to a new lecture of this wave optic series. In this lecture, we will be discussing about the superposition or interference of two waves. Okay, so in the previous lecture, we had discussed that how the two propagating waves propagating in same direction they interfere, and we had obtained the variation of energy density along the path of propagation, and how the potential energy changes, and how the kinetic energy changes, and how the total energy changes when two traveling waves interfere in the same direction. Here in this lecture, we will see that how two light waves they get interfere by using two point sources. In case of sound wave, when we use two point sources to get an interference, there will be no much difficulty, because when we use two independent sound waves, then there will be a specific phase relation between the two waves. And in case of microwave also, there will be a specific phase relation for two independent sources or two independent point sources. But this is not the same case in case of light, because due to the very process of propagation, or we can say due to the very process of emission, the frequency of the light waves get changing time to time. As a result, the process of interference happen. Although the process of interference happen, we cannot observe this process, because, and what is its cause? Its cause is due to the very process of propagation, or due to the very process of emission, the the frequency of the light waves they get changing with respect to time. So, to get interference pattern, we have to get a single frequency. We have to get two sources having a single frequency. How can we get two sources having a single frequency? The one method is we consider two apparent sources which are made up of, or which are created by a single source, and there are different processes in which we can obtain two separate sources from a single source, and the different process will be discussed in the later lectures. But the main process is, or the main idea is to get two apparent sources from a single source. Then only we can get a particular frequency or a constant frequency between the two sources, and we can, as a result, we can get a particular interference pattern. Otherwise, although the interference will be happen, but we cannot observe it. So, why I am saying this? Why due to the variation of intensity? Sorry, why due to the variation of frequency, the interference pattern will not be observed? Let's see. As we have discussed, let here two independent equations. One is given by y is equal to a1 sin kx minus omega t, and another equation is, let's say this is y1, y2, that is, so these are two independent equations, so we should not mention here y1 or y2, simply we mention here y. Another equation is given by y is equal to a2 sin kx minus omega t. Here amplitude is a1, here amplitude is a2. Here these two equations are two independent equations. Okay. This equation, the first equation says that a particle situated at a distance x from the source will be displaced by this much distance from the mean position at time t. And similarly, this equation says that a particle present at a distance x from the second source will be disturbed from the mean position by this much distance at a time t. So let here is source S1 and here is source S2, and the point at which we are eager to get the interference pattern, let's say the point is here E. At this point situated at a distance x, this point is situated at a distance x from source S1, and the second source S2 is situated at a distance x plus del x, So according to this equation, fits pretty much in this condition, because in this condition the source S1 or the point P is situated at exactly x distance from the source. So if we put this condition in the first equation, we will get the displacement of the particle due to source 1 will be y1, that is equal to a1 sin kx minus omega t. Coming to the second source, the point P is situated at a distance x plus del x from the second source, and the condition of second source is that it says that whenever a particle is situated at a distance x, then it will be disturbed through this much at time t. And fortunately, here the particle is situated at a distance x plus del x. So the displacement will be y2. So displacement at time t will be y2, which is equal to a2 sin k x plus delta x minus omega t. Here, if we separate the delta x, sin kx minus omega t, and here the extra term is k into delta x. Separating the extra term k into delta x. Here the value of k is 2 pi by lambda. This is wave vector. That is a2 sin kx minus omega t plus 2 pi by lambda into del x. So the phase difference between the two sources at point P is 2 pi by lambda into delta x, where delta x is the path difference. Here we can see that the phase difference is constant, because 2 pi is constant, lambda is constant, and there is a constant phase difference delta x. But in the practical case, the frequency of the light wave does not remain the same due to the very process of emission of light photons. So let us consider the second light source is emanating or propagating a light wave having a frequency varying from minus delta to plus delta. So the frequency of the first source is given by omega, and the frequency of the second wave will be given by the frequency of the first wave. I am writing here frequency of the first wave. Let take the frequency of the first wave be constant. So frequency of first wave, it does not mean that frequency of the first wave will be constant, because this is also a light wave and its frequency will also change. Here we are taking the case, let the one frequency, the source or the frequency of one source is constant, and another source, frequency of another source is changing. If we take the frequencies of two sources are changing, then the case will be same. Interference pattern will occur and we cannot observe the interference pattern. Here, for simplicity, we are taking the frequency of one source is constant and the frequency of another source is varying with respect to time. So frequency of first source, is equal to omega, and frequency of second source, that is equal to omega. There will be extra term plus minus del omega, which means the frequency of the second source is not constant, it is varying within a range omega plus del omega to omega minus del omega, and this variation is with respect to time, which means del omega varies with respect to time. So del omega must be a function of time. So the frequency of the second wave can be written as omega plus minus f of t, because del omega varies with respect to time. If we put this condition in this case, let's see what we will get. Here the condition is same. The point P where we are wishing to get the interference pattern is situated at a distance x from source S1 and from source S2 at a distance x plus del s. In case of the source 1, the particle will be displaced by this much distance at time t. Y1 is equal to A1 sin kx minus omega t. This is okay. Coming to the second source, due to the influence of second source, the particle at t will displace some distance, and what is that distance? That distance will be according to the second equation. The second equation says that whenever a particle is situated at a distance x, then it will be disturbed by this much value. So the distance here in this case is x plus del s. So here we are going to replace the x by x plus del s. So y2 will be equal to a2 sin k x plus del x minus here omega is varying from omega minus del omega to omega plus del omega. So omega plus minus del omega, and we have taken the value of del omega is a function of time. With respect to time, it is varying. Okay. Then I am going to separate the x term and t term. Y2 sin kx minus omega t plus k into delta x means 2 pi by lambda into delta x. Here this is minus, so minus will be plus and minus plus will be minus or minus plus f of t. So here this term is the phase difference. So the phase difference delta is equal to 2 pi by lambda into del x minus plus f of t. So this is the phase difference. Here we can say that or here we can see that the phase difference delta is changing with respect to time. But in the previous case, the phase difference delta was only 2 pi by lambda into delta x. But in this case, the expression of delta is this, which means the phase difference changes with respect to time. So at a particular point, the phase difference will change with respect to time. So we cannot say that at a particular point we will get a dark fringe or bright fringe. Instead of getting a dark fringe or bright fringe, we will get something extra here. So from this we knew that for a light source we have to get two separate sources having a particular frequency relation or having a constant phase relationship. Otherwise, we cannot observe the interference pattern. However, there is so much methods from which we can get this type of condition, or we can get two apparent light sources by using a single light source. Okay, so this is the thing. Next, we will discuss that how and what are the process. Part of the process we will discuss in the later lectures. But the process of getting this interference pattern is broadly categorized into two categories. One category is division of wavefront and another category is division of amplitude. What is the division of wavefront? When we are using a single source to get two apparent sources, in this process a wavefront coming from a single source is falling on two equally spaced holes or two closely spaced holes, and as a result from these two closely spaced holes there emanates two new wavefronts according to the Huygens principle, which says that every point in a primary wavefront acts as a secondary wavefront. Let's see how it happens. So this is a light source S. I have said that the wavefront coming from a light source S falls on two closely spaced holes. Let's say these holes are here. One hole. This is the second hole. Wavefront is coming from this light source. When the wavefront falls on, here the slit S1 and the slit S2. When this wavefront falls on these two closely spaced slits, then from these two slits, two separate wavefront emanates. And this process is called division of wavefront, because initial condition there was only one wavefront, and after falling that wavefront on these two slits, two new wavefronts generated. So we can say that the one wavefront is subdivided into two wavefronts. So this process or this method is called division of wavefront. And another method to get interference pattern is division of amplitude, which we will discuss in later lecture. In division of amplitude, what we do in this process, the light wave or the light ray gets reflected at several surfaces, and due to the reflection, its intensity reduces. And why the intensity reduces? Because we know that the intensity is directly proportional to amplitude, and as the intensity reduces, we can say that the amplitude reduces. Here the amplitude is subdivided. into several parts. This process, how this process happens, we will learn about in the following lectures. However, we can emphasize that all the present lecture and in the following lecture, all the interference pattern or all the interference process are based on the very popular theory of principle of superposition, which says that whenever at a particular point two or more waves interfere, the net disturbance at that point is the vector sum of the several disturbances when either source is absent. This is the very important concept of superposition of principle, and all our findings and all our observations will be based on superposition principle, which we will discuss in the next lecture.